Okay, let me see why the microphone is, let me see. Yeah, seems to be. Okay. I think that you can hear me nevertheless. Thank you to be here for the lecture of today. As I told you, don't care about the date of which you can read here, because it's a lecture which belongs to the background, in the sense I didn't change the content, in the sense here. Okay, do you remember a little bit this concept here of the definition of the projection? I don't want now to repeat again this part here. We will see in some exercise eventually. Probably I would like to spend really a few words about this slide, in which we can see here a possible expression, which basically starts, if you want, from let me say, from a definition of cosine function, but which basically is here. But in general, the idea was to connect. If I don't know if you remember this Schwarz inequality in the context of the cosine function. And cosine function is nevertheless related to, or at least the definition is related to a triangular and a rectangular and triangular with an angle with 90 degrees, let me say so. Of course, yeah. And no, it's okay, excuse me, but stage. Okay, you're right. Thank you for informing me. Yeah, thank you. The idea is everything is in this sense known, but please pay attention. It's known if we are considering the dot norm, let me say, or that the L2 norm, no? At the end, we called this norm, this distance, you remember, norm equals distance, L2 norm or the dot norm. Of course, if the norm is different, also the concept of the cosine and also different aspects of our algebra changes. This means also, do you remember the Pythagoras theorems and so on? I would like to give you just a feeling, because of course the examination is not exactly on these topics here. Or of course I can now I will do the exercise. I can propose, for instance, in the exam, please demonstrate that all points which lie on the red, let me say, figure, have the distance equal 1 in this case here. This means in the context of a possible definition of the circle, which is the set of the point with the same distance with respect to the point which you call the center, is in a circle. The red figure is in a circle. In the same sense, you remember last time I told you the green figure is in a circle. This, of course, everybody can understand, and everybody agrees that this is in a cycle, because we are habit to work which is a kind of metric. The black is also a circle. In this sense, I have a couple of exercises to show you. I will approach them. You have to just follow me. I hope to find, in order to show you analytically a little bit better this concept here. Even though you remember last time I show you that, for instance, in accordance with the L2 norm as a distance, and a different way to define a distance. I mean, we are habit with this norm. With this norm, we can show, probably I have also here, we can show for all these green points, let me see, so they have the same distance with respect to this point here. Notice it. If I apply this, I have here, I'll show you this definition here, I can show you this. But you believe me also without demonstration. I see that this is the cycle, but I will tell you now again that the red figure, the red set is also a cycle, and also the black. The black, we don't need to do many calculations because if you look about, if you think about the definition of a distance in this form here, which I consider the max component of the vector. You remember vector or the vectors equal points. Do you remember? For us, in our definition, in this room, it's the same. Also in this room, also these three figures can be the same. Same, what does it mean? The same. Can be called cycles if I consider different norms. Look, the third one, we don't need to do mathematics because if you consider all these points here and this line here, which are characterized by the coordinate x, let me say x equal 1 or that, a1 equal 1 if you want to reconsider this definition here, and y which changes from 0 to 1 is, of course, if the distance is defined as the maximal component in absolute value, all these points, the distance of all these points with respect to this point here is 1. And you can do the same here, because here now, as I told you, the y distance does not change, it is 1, but the x is the maximal here, 1, and then will decrease until here. I can go ahead. I mean, this point here, in accordance to the definition of the distance, let me say number 3, L infinite, this point here, with respect to this point here, the same distance with respect to this, with respect to this, with respect, if the distance is this one. It's just a way to represent our, our reality. Because I see these three figures. When I can use this? Okay, I don't know if in this course we can apply, because the applications with different norms is quite complicated in the sense when we use different norms in cases we have a really complex phenomena. I told you last time that we used, for instance, to detect noise, and then the norm, which is the name of the norm, is semi-norm. Okay, let me see if I find this exercise for you. In order to show you a little bit more in depth, and then I will upload. I should have it. Okay, I found it. Yeah. Look. Now I will show you, for instance, here. Let me stay here. One second. Yeah. Now come. Should come. Yeah. Excuse me for this delay. Oh. Yeah, now. Let me see if there is something. I better. Okay, look at this again. This three, or this picture with these three possible cycles. The definitions, I don't need to look at this. Let's consider the red line on the first quadrant. This means this. this line here. Look, this line here can be mathematically, I don't know if you remember in gymnasium, this basically we can reconsider. I will come back on this topic when we consider the analytical geometry. But in any case, look, we have this line here passing through point 1, 0 and 0, 1, which can be written, believe me at this moment, believe me, in this formula, y equals minus x plus 1. I will do that in detail when we attack the problem or the chapter of analytical geometry. But at this moment, believe me, probably some of you remember a little bit from gymnasium. But of course, this is valid. Please pay attention to the word. This representation is valid in the context of this set just if x is between 0 and 1. Otherwise, we have to reconsider the different expression. Try to do at home, but I show you how now for each x, and not only for this point here. Do you remember last time I told you this point here, the x coordinate of this point here is 1 divided 2. The y coordinate of this point here is y divided 2. If I consider now this is a possible definition of the distance, 1 divided 2 plus 1 divided 2 equal 1. This means the distance of this point here is 1 with respect to this here. Because the coordinate is 1 divided 2, and here I didn't put it at 1 divided 2 in terms of y. This means the distance of this point with respect to this point is 1, as this. The same distance. It seems to be not the same, because we are habit to think about in terms of Pythagorean theorem. We are habit to think about in terms of this green circle metric. But believe me, that this is the same. Now, it seems to be strange, because if I have to move from here to here, and if I have to move from here to here, when I say that this will be the same, the people can say, but we are crazy. Because of course, I need, with the same velocity, more time, I need with the same velocity, in the sense, more gasoline, because it seems to be longer. Please pay attention. This is how possible to say. If I say so, I have to say that the physical phenomenon, or at least what I am telling you about now, about the distance in terms of velocity, in terms of movements, can be better, let me say, explained or better described, a very important word, with the L2 norms. Because I realized that I need more time if I validate what I am trying to explain. It seems to be this is not the same distance. Because if they have the same velocity in both cases, I can measure the time, and I say it seems to be this is what you're saying is not correct. No? Because we know from physics that in an uniform movement, the position equals v velocity multiplied by the time. I don't know if you remember physics. Yeah. This does not mean what I have told you is not valid. Excuse me, is not true. This just means that is not valid in the context of this physical phenomenon. Therefore, you remember I told you we used a distance in the metric which is not validated Pythagorean theorem, because we have to describe in a reality extremely complex, which is not the movement of an object and so on. It is not the classical mechanical, let me say, approach. In fact, this kind of matrix, this kind of new geometry was used, or let me say, it is used in phenomena very complex, for instance, interatomic phenomena, in which the physics, in which think about the current. You know the current. We have here the current. The current can be seen can be imaged. The current has some electrons which is moving from the position to another one. But this really is a model which is not always explain what happens in the electrical system. If you think about the wave theory of the current, this is totally different in to explain some phenomena. The Pythagorean theorem, or better to say, the L2 norm, does not help, or better to say, is not valid, in the sense does not reflect the phenomena which you want to observe, which you want to describe. Now, if you want to describe a movement of the object, it's clear that can be validated by the metric, which is, I told you, this L2 metric in the sense. This means the kind of norm which we want to use depends on what I have to describe. This means nobody is true, could be valid or validated by the phenomena which you want to describe. Okay. Let me do analytically the calculations. Look, the period in this interval, 0, 1, are characterized by x coordinate equal x, and the y coordinate equals minus x plus 1. I don't know if it's this way to say can be understood. For each x, which is, let me say so, which is moving here from 0 to 1, this remains fixed. Y is moving minus x plus 1. At 0, I am here. Excuse me, I am moving in the wrong direction. At 0, I am here. For x equals 0, I am here. Look. For x equals 0, I am this point here. Moving x in this direction, I will, let me say, cover all this point. And for x equal 1, I am here. This means all these points in this interval are characterized by this vector. Please pay attention. Is a vector characterized by two functions. The first function is x, and the second function is minus x plus 1. I don't know if it's a little bit abstract, but we can understand. It's a vector, yeah, but it's a vector of functions, because we want to characterize a set of points. Try to abstract your thinking. Huh? Now, look at this. If I apply the definition, which I wrote directly again here, this means in L1 metric, metric means, metric, you know, the word metric. In German, I don't know how to say metric, the same word probably. Metric. In a system which I measure. Again, the idea of this lecture is not necessarily the Pythagorean theorem, which is based on the norm L2, is valid. Depends what you want to describe. Of course, if you want to describe in a cork which is moving in this room, it's more suitable the L2 norm or the L2 metric. It's not different metric. This implies absolute value of x plus absolute value of minus x plus 1. Why that? Because the vector AI in this notation is characterized by A1x, A2 minus x plus 1. Try to think in abstract form. Too difficult? We have two components, A1 and A2, in accordance with this definition, nomenclature. What is A1? Is x, the first component. 1 characterizes the first component. What is A2? Is the same component. Should be better to say P1 and P2 in accordance with this nomenclature, but we can understand what I intend, you know, because in books very often we write A. You know? Here, P is points, you know, of the set. Did you agree with this? But here, let me see if I have a better explanation. But why this is, let me see if I have a better explanation of yeah, why this is basically 1. I don't know if it's clear why it is 1. Because x between 0 and 1 equal x. Do you agree? And also here, minus x between 0 is 1 is again x. I probably I have something better to show you so we can understand. Let me see if I do the calculation more in depth. So we can understand, I don't find quickly. Probably I don't find. Actually, because I would like to skip to right. 1 second. I have, but I don't find. Let me see here. I can try to explain without. Yeah, I show you. Why? I show you here. I didn't find, but anyway, look. I have to explain why this is 1 for each x if x is included in 0, 1. Yeah, why that? Because this is positive inside. This means in 0, 4, let me say mathematically better. It is clear, no? For each x included in 0, 1. Do you remember in gymnasium the meaning of this? This means if it's 0, 1 is x, if it's negative is minus x. But also this can be written equals minus x plus 1 if for each, excuse me, or if you want, for each x including in 0, 1 is trivial because this is never negative. What is inside the absolute value is never negative if we have this condition. This means x minus x plus 1 is equal to 1 for each x included in 0, 1. Trivial. No? Let me see if I find quickly an exercise in another segment in this sense, in order to show you how we can do. Otherwise, I leave you as an exercise at home, because I would like to go ahead with the program. But believe me, think about always as this concept here. Consider the hypothesis. No? The hypothesis is that x belongs in some interval, 0, 1, or minus 1, 0. We don't have other interval. Let me see if I find, should be nice. I have somewhere, but I should go to find now, but let me see. Over. Could be. I don't find it, doesn't matter. I give you an exercise to do at home. Next time, if I find so many exercise, sometimes it's difficult to find where this is. Okay, I don't want to invest more energy. I show you. I give you an exercise to do at home. Try to demonstrate that, let me say, try to demonstrate that if y equals, let me consider now, which what do you want? Is here? If y in the sense is equals x plus 1, I don't know if you remember how we can build this line here. We'll come back on this when we do the analytical geometry. This line here is characterized by x and y plus 1. This point here, I don't know if in gymnasium, but I will come back on this later. For x, which belong to -1, 0 in this case, we demonstrate this implies that L1 norm is equal again what? Remember, no? L1 norm is, I told you before, we consider something like that. No? Remember this. With a vector A, let me see, a vector A is exactly as in the lecture. Which a vector A capitalized, which consists of A1 and A2 not capitalized. You remember this? Exactly as I told you before. Try to do this. We will see with the same considerations which we did in this case. It's not different. We will see that as one. And if you want, you can try also for this segment here, for this segment here. If I find next time, I will show you the solution. But believe me, it's extremely easy. Huh? The consideration is always the same. Here, the point here is characterized, point red this time, is characterized by x and x plus 1, 2 components. And then you have just to think about the interval of x. But it's clear that will be 1, because here we change the sign of the interval, but we change also the sign of the coordinate x intuitively. Okay, let me go ahead with another chapter. Before going ahead, nevertheless, a few words considering the last slide, and just one word, or the few words in which we use this kind of metric in the problem with my PhD students, of course, for the exam, just a mathematical exercise, eventually something like that, in order to, let me see, yeah, the idea of this part here to give you a feeling that the reality can be described in different way, but the problem is what is valid. Is valid what when we can say that one metric or an approach, the sense is valid if somehow explain what we are observing. If we have a matching between what we are observing and what we are describing with mathematical language. And this means, of course, it seems to be in accordance with what I told you before. If I have to describe a movement, a mechanical movement on an object, at least in macroscopic form, it seems to be that L square seems to be norm. In particular, do you remember, as I told you, gasoline in terms of energy in macroscopic form, it seems to be more suitable because it reflects our experience. But believe me, in interatomic dynamics, it's totally different. The example of the current, we have a different way to represent the current. Electrons, which is moving from a point A and point B, this is a particle model, which we can think about governed by the mechanical law, but also wave theory. I don't know if you hear about that. Poincaré geometry, Einstein approach in the relativity of, this means you can understand that can be used for describe a different reality. Here, to conclude, we used this norm, which is not Pythagoras theorem. Absolutely. We cannot demonstrate that Pythagoras theorem works in this context. We use this to detect noise, to detect errors in signals. We can see that we didn't try to describe a movement on an object from a point A to a point B, because probably this metric here a little bit contradicts what we perceive. Do you remember the example of gasoline or time, which I need to achieve Hanover from Lüneburg? Of course, it seems to be that the metric, the Pythagorean norm or the L2 norm explain better, no? Because reflects what we can measure. Measure, metric, the same root. No? The word metric, measure, the same root. Okay, let me open now. Let me open now the second presentation, which you have in my study already. Looks like something like that. Let me see, where is he? Let me drink in the meantime something. Okay, let me share. You can see also, let me share. I didn't do it. Now. Again, you can see here an old datum, yeah, date, but because again, it's not just background. Yeah. Do you remember this? I already told you about the orthogonality. No? I already introduced the concept, this concept. Yeah, we can see here how with this concept here we can derive in the context of our norm the Pythagorean theorem, because if you remember a little bit these calculations which we do together, and then of course if A is orthogonal to B, we collapse this in the Pythagorean theorem. In accordance with, of course, the definition of the orthogonality, because A dot B somehow equals 0. Exactly. This is just a repetition. I would like to skip this. We have seen again today in the morning, which came basically from the Pythagorean theorem, because it's based on the concept of the orthogonality of A and B. Now, more important today is this one, because it's new. No? And we will see together some exam exercise. Linear combination of vectors. We have a first definition here. Let me move this. We say that X is called a linear combination of vectors, or we can say, we can consider set of vectors. That is, I think this is more appropriate in this language. Generally, combination of vectors, combination of set of vectors. Anyway, we have vectors, no? to simplify the notation. We can be seen in a set. We can see here AI with I from 1 until n. This is the set of this vector here. If, please remember, if in the definition means if and only if. This means if X equal sum of alpha I multiply I AI from I starting from 1 to m, in which alpha I are scalar, we say basically in a combination if exist, let me say alpha AI scalar, and we say that X is a linear combination of this vectorial alpha. Let me say easy. Basically, if I have alpha scalar, the combination of in this form here of my vectors, which can be organized in a set, is called, very important, it's called, just a nomenclature, a linear combination. Again, if I have this, X in a linear combination. X in a linear combination is if X, excuse me, can be expressed in this form. Now, please pay attention here. This is extremely important because here allows with the definition number 2, which is based on the definition number 1, to do some exercises. Extremely important, this exercise, also in applications. We say that the set of vector AI with I equal 1 from 1 until m, again, m vectors, are linear independent. Here I put it if and only if, but it's not necessary. No? It's not necessary. Inside the definition, very often we write just if. This means they are linear independent if this condition holds, but it holds, we can say the same if this condition holds. This says to us that the set of vectors are independent. This means just the definition. Sometimes we have if and only if, sometimes just if, because the definition works in both directions. We will do some consideration on this condition here. Look, the condition says that the set of vectors are independent if basically the linear combination, my X, is equal 0, but must be equal 0 for all, it's realized, let me say, if all parameter alpha are 0. Very important consideration. We say that they are independent if X as a linear combination of this vector is 0, but with all alpha equals 0. We say in some books, we can find this sentence here. This means that a set AI generates the vector 0, generates, very important, generates the vector 0 only in a trivial way. Trivial means all 0. Let me do a couple of exercises. Exam exercise. This is a remark. Before doing exercise, let me do this remark. Look at this set here. 2, 0, 0, 3, alpha, beta. We can see it's written here that this set is depending set because we have a vector here which consists of 2 parameters, alpha and beta. Look at this. We have basically 3 vectors. Let me say 3 vectors because alpha beta could be a very real value. But 3 vectors included in dimension 2. I mean, n here is equals 2 because this, remember this I told you, all these vectors are characterized by 2 components. Very important, I didn't clarify this point here. Each set of vectors is in a set, the sense is in a set if the dimension is the same for all vectors. I mean, I cannot include in a set, I can do, but no meaning in the set vector with 2 components and vector with 3 components, vector with 100 components. We speak about set of vectors. Now, if the vectors consist of the same number of components. This means, look here, belonging to R up to N. In this case, N is equal to, is the number of components. First component, second component, first component, second component. The components must be, the number of the component must be the same. Otherwise, we cannot speak about set in the consistent way. Now, it seems interesting, this remark here, because if M, the number of elements of the set, number of vectors, is strictly larger than the number of the, dimension. I told you about the dimension a couple of weeks ago. Directly, we can say that the set is a set of dependent elements. We can demonstrate it. It's easy to see with a demonstration, with a mathematical demonstration. I will show you. Intuitively, it's not so difficult to remember this because somehow we have a set too crowded for an element. I mean, the number of elements exceed the number, the dimension of the space. This means it's intuitive to think that we have a dependence. We will see a little bit in detail. But we can imagine that there is possible, we can keep this sentence here. It's a theorem. We can demonstrate this theorem. It's a proposition. What happens if m is, let me say, no more than n? This means less or equal. No more, no? Less or equal. And we cannot say what happens because the system, the space is not so crowded. Let me give you an intuitive interpretation. This means here, for each alpha, beta real, for each alpha, beta real, the system is dependent because we have 3 elements in a space with 2 dimensions. This can help in the exam, can help in the exercise. We will see directly now in a possible, exercise. Let me see, let me think if I forgot to say something. I think if I let me go ahead, probably I will add something to you later. Look, exam exercise. I don't know if I have the solutions here. Yeah, I have it. Look, exam exercise. Yeah, 3 vectors. And the dimension of the space in which these 3 vectors are included is 3, because each vector consists of 3 components. V1 is 1, 2, 3, V2 is -1, 3, -1, V3 is 0, 0, 1. Question, exam question. Are these 3 vectors linearly dependent or are these 3 vectors linearly independent? This means we have to discuss the dependence. Did you already see this example, this exercise in Math 1, Math 2? No. But it's easy because math, believe me, it is easy because we have the definitions and we apply the definition. We know what is, we already define the concept of dependence or independence. We already know what I intend with this word. Very often in math, it's difficult to understand what the other intend. The definition is clear and we apply the definition. But we can answer directly if you consider the remark. We cannot, because we have 3 vectors in 3 dimensions. This means, is this case here? Did you agree? If here I put another vector, of course, they are dependent. But you have 3 vectors in the dimension number 3. Let me go ahead. This is the answer for the example. If you remember the definition, we have to verify if the linear combination x equals 0 is generated by alpha, I1, alpha 2, and alpha 3 in our case, m equals 3, with all alpha equals 0. If all alpha, alpha 1, alpha 2, alpha 2 equal all alphas, no? Equals 0, then we say they are independent. You remember this? Again, of the definition. The definition we'll put in the data sheet, this here. They are independent if all are 0. Let me do the calculation with you here in the slide. Applying the definition means alpha 1, which multiply V1. V1 was 1, 2, 3, plus alpha 2, which multiply V2. V2 was minus 1, 3, minus 1, plus alpha 3, which multiply 0, 0, 1, should generate, you remember the word generate, 0, 0, 0. Remember this at the end of the definition of can be used also this way to say. Now, at the beginning of the course, I told you what we intend with this sentence here. You remember? And a parameter which multiply a vector, which means that this parameter multiply this coefficient, and this coefficient. The same for this, the same for this. Then the sum between vectors is the sum of the corresponding components. This means alpha 1 minus alpha 2 plus 0 multiply alpha 3 equals 0, because I defined also in our algebra what is the meaning of equality between two vectors. I mean, the left part here is the vector, because the sum of vectors is again a vector. Do you remember this? The first component of this vector on the left part is alpha 1 minus 2 alpha 2 plus alpha 3 multiply 0, which must be equal to the first component of the right. Therefore, I wrote here this equation. I don't know if it's easy to intuitive somehow, but it's based, if you think from the intuitive definition, which I told you about sum of vectors, multiplication of vector by a constant, and equality of two vectors. We have a vectors on the left, which is resulting vector of these operations. And in the right, we have the fixed vector 0, 0, 0. I can say the same for the second component. I can say the same for the component number 3. Question here? I think in the exam, no problems, no? Or it's difficult to follow me in this. I don't think so. No, it's intuitive. I don't. Now, let me do some calculations here. We don't need to do many calculations, but we can see, for instance, this is alpha 1 minus alpha 2 equals 0. Here we have 2 alpha 1 plus 2 alpha 3 equals 0. And here we have 3 alpha 1 minus alpha 2 plus alpha 3 equals 0. Nevertheless, from the first equation, I can say that alpha 1 is equals alpha 2. We can see from here. Because alpha 1 minus alpha 2 is equal to 0. This means alpha 1 equal alpha 2. Did you agree? Now, is alpha 1 is equal alpha 2? Look, the second equation remain minus 2 alpha 1 plus 3 2 alpha 2. But if you think about, let me say, this position here, this alpha 1 is equal alpha 2. If you think about the alpha 1 is equal alpha 2, we have here 2 times alpha 1 plus 3 times alpha 1. Do you remember? Because we have this. If you replace here, do you remember insertion methods, plugging in? You have 5 times alpha 1 equals 0. This implies alpha 1 equals 0. I don't know if it's clear. If you plug in alpha 2 here, alpha 2 is equal alpha 1. This means 5 times alpha 1 equals 0. This means alpha 1 equals 0. If alpha 1 equals 0, from this equation here, we have with us also alpha 2 equals 0. Clear, no? Because alpha 1 is equal to alpha 2. Now, if you look at the equation number 3, which we have alpha 1 and alpha 2 equals 0, we have 0 here, we have 0 here, we have alpha 3 equals 0. Conclusion. This means that the given set of vectors represents a linearly independent set, because all parameters, alpha parameters, equal 0. Did you agree? Exam, one comment, no? Come on. Let me do something more easy sets. Look at this 3 vector, V1, V2 and V3, in your opinion, are dependent or independent? In the first case, no, the notation is not so not so nice, but let me consider the first line V1, V2, and V3, three vectors, and a set of vectors, which consists of V1, V2, and V3. And then we have also the second set V1, V2, and V3 in the second line. In your opinion, these three vectors are dependent or is not? Or is not? Are independent or is not? Better to formulate in this form. We have three vectors in space dimension 2. The same condition, the same situation here. Huh? This means I can formulate for both the same question. Should I do the calculation mathematically? Yeah. Again, for students who already seen, probably is boring, but I realize that not for everybody is boring. I do it. Yes. Okay, I understood you. The question is here. We can consider let me say the first one or the second one. The procedure is the same, no? Three vectors in dimension 2. But intuitively, we have also the solution. No? Intuitively, we know that we are waiting for an independence because we have three elements, three vectors, V1, V2, V3, is in the dimension which is too crowded, feeling too crowded. We can also formally demonstrate, but how we can formally demonstrate? I am considering n dimensions, means A1, A2, A3, A4, and then AN, another vector B capitalized B1, B2, dot, 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 Bn, and then I can do the demonstration that if the elements of the set, the number of the set is larger than the dimension of the space, we have the dependence. Let me show you in this case without doing the formal demonstration. But we cannot make mistakes in the exam because we know that I am waiting for something dependent. I copy and then I will share. No? 1 second. Let me consider the first one, no? But you can consider also at home the second. I copy and then I come to you. Okay. I try to do a little bit. Let me share now. Yeah. Is the set V characterized V1, V2, and V3. This means, you remember, definition. I check the dependence or independent using the definition. This is the definition. This is X, no? 0. Definition number 2. Look again on the left. Okay, applying this. Excuse me, alpha, no? Exactly as in the definition. M elements, M equal 3, the dimension N equal 2. Let me do now exactly the application of the definition. Please pay attention. This 0 is in a vector, no? This 0 is in a vector. To be formal, sometimes we indicate with the line, but it's not necessary. It's in a vector in the dimension N equal 2. This means something like that. This means alpha 1, which multiply V1, alpha 2, which multiply V2, alpha 3, plus, of course, everything, no? Formally. But of course, in the exam, you don't need to waste time to do. Now I am in the lecture to explain what I am doing. You have to just directly write what? You have to write this sentence here. right? Correct. Now, as I told you before, 0 is equal alpha 1 plus alpha 2 plus 2 times alpha 3. 0 equals, let me write formally. Alpha 1 multiply 0 plus alpha 2. If you want to multiply 1, but let me minus alpha 3. Please, to be formal, or formally correct, I have to put this symbol here because the equality, what is the meaning of this symbol here? Because the equality between two vectors, and I am doing now the equality between two vectors, involves all components, first component and the second component. This symbol here in math means and. You remember in gymnasium, means and. You understand and? Und, no, in German, and. Because the equality means each component must be equal. And each means both, they say. Components. Excuse me, for somebody probably is boring. But the idea is how the words reflects the mathematical meaning, the mathematical way to proceed. Math is also in the language. This is a little bit the idea of this course here, to go in depth also in the language, not only 1 plus 1, 2 plus 2. This is already done probably. And sometimes we did, and then we try to understand a little bit more in depth what we did. Okay. Mistakes? No, I don't think so. No? What we can say here, for instance, from the second equation, I can say that alpha 2 is equal to alpha 3. Did you agree? No? Because this is here. I can now combine this information here. This means I can write here 0 equals, for instance, alpha 1. If you replace, I don't know, alpha 2 equals alpha 3, we have this. But this here, excuse me for this notation, but can help in any case. I can write something like that. Did you agree? This means from here we have alpha 1 equals minus 3 times alpha 3. And considering this, we have alpha 2 equal alpha 3 for each alpha 3, for instance. This is the result. Again, alpha 1 equals minus 3 alpha 3, and alpha 2 equal alpha 3. I don't know if I made a mistake. Please correct me if I made a mistake. I don't think so, no? Please, very important this concept here, for each alpha 3. Did you agree about that? If I made mistake, correct, please. What is the meaning here? The meaning is directly the conclusion that not all for alpha 1, not necessary for alpha 1 equals 0, alpha 2 equals 0, alpha 3 equals 0, we have 0. For instance, here, we can see that for each alpha 3, not only for alpha 3 equals 0. I write this conclusion. Not only for alpha 3 equals 0, we have x equals 0. X is the linear combination. But for each alpha 3, this means alpha must not be necessarily 0. Alpha I, alpha 1, alpha 2, alpha 3. X, the linear combination. That was the definition. But for each alpha 3, including also this condition here. Let me write better. For each alpha 3 such that alpha 1 equals minus 3 alpha 3 and alpha 2 equal alpha 3. This means if these two conditions are satisfied, and these two conditions are satisfied not only for alpha 3 equals 0, these conditions, I can take, for instance, alpha 3 equal 1, whatever. For each, if I consider alpha 2 equal minus 3, excuse me, alpha 1 equals minus 3, and alpha 2 equal 1, I will obtain x equals 0. This means not necessarily all elements are 0. Okay. But we knew because I already told you intuitively this property, we have more elements, the number of elements is larger than the dimension of the space. Try to do at home the exercise number 2. Quickly now, intuitively, if I have a set of which consists of V1 and V2 in this form here, dimension is 3, in your opinion, dependent or independent? We can see here directly the answer. They are independent, of course. I have to verify because we have two elements in a space with dimension 3. This means I cannot say directly. I cannot say directly. I have to verify mathematically. But if you remember the method which we apply now, no? to in this case here, it seems to be quite clear because these two components are 0. This means we don't have the possibility to have independence because I cannot, I can annihilate the second component and the third component just with parameter 0. I don't know if it's visible here. Here we can understand from this. 1, 0, 0 and 2, 0, 0, V1, 1, 0, 0 and V2, 0, 0 are dependent because we can see here to annihilate the sum of V1 and V2, we find, to annihilate the sum of V1 and V2, we find a condition to annihilate. Look, we can see directly alpha 1 which multiply 1 plus alpha 2 which multiply 2 equals 0. But it's clear this. Alpha 1 is equal minus 2 alpha 2. Should I write? Because these two components are already annihilated. It's not the case here. Should I do this easy example for you? Sometimes in the exam, intuitively, we already image which kind of solution we have. Now, here is easy. I can start from here. Apply the definition. Vector 0, 0, 0 equals alpha 1 which multiply 1, 0, 0 in column form plus alpha 2 which multiply 0, 0. The second two components state identity, 0 equals 0. This means I don't have to do anything. I show you if you want. Let me copy. The second case can explain the first. I come to you. Now, are these two vectors dependent, for instance? Yeah, apply the definition. directly, no, or without repeating everything, no? Directly. In the exam, you have to directly write. So I try to tell you directly with the words. Now it is easy. Look, 0 is equal alpha 1 plus 2 times alpha 2. From the second and third equation, we have 0 equals 0, 0 equals 0. This for each alpha 1, for each alpha 2. Very important, this sentence here. It seems to be useless, but it's very important, because 0 is equal 0 is valid without conditions. I don't have to justify. This means in our context, we are looking for alpha I, we are looking for alphas. Please pay attention to the words. We are looking for alphas. But 0 equals 0 does not depend on the choice of alpha. This means I have to write this. Please, in math, we write everything. 0 equals 0 for each alpha 1 and alpha 2. Nobody asks why 0 equals 0. I mean, here and here. It seems to be trivial, but I try to introduce this language. Look here. This had an interesting solution. For each alpha 2. This means if I apply this condition here, I can find, I found any condition, and I can say that not for all alphas 0, we generate this vector 0. These two components, yes. But the first component, not necessarily alpha 2 must be 0. Here for each, excuse me, but here not necessarily should be 0. If it's 0, alpha 1 is also 0, but if alpha 2 is 1, for alpha 1 equals minus 1, I have a 0. This means not all elements of each alpha are 0. The vectors are dependent. Do you agree? Because not necessarily all parameter alpha are 0. Dependent. The vectors are dependent. Not each alpha must be 0 to obtain 0. For instance, alpha equal 1, alpha 2 equal 1, alpha 1 is equal to minus 1, minus 2. If alpha 1 equals minus 2, as I told you, and alpha 1 is equal 1, we have 0, 0, 0 everywhere. It's not necessarily all. Because we have a dependence. The dependence is this. This is the dependence. Alpha 1 depends on alpha 2. You can write also alpha 2, which depends on alpha 1. If you write alpha 2 equals minus 1 divided 2, minus 1 divided 2, multiply alpha 1. I don't know if with the word is more complex than to write. If you consider now the exercise, the first exercise, they are independent. Should I do it? It's boring now, no? It's clear. But intuitively, very important, the exam, or when we apply in our research field, we do that. Later, I clarify when we do that. Very often with the vector of functions, but the concept is the same. We look at the value. We look at the value. Here, why they are independent? Because we cannot get the second and third component 0 if the vector are not 0. I don't know, probably it's not clear to everybody this. Basically, V1 and V2, they are not in the same line. If you look at these two vectors, they lie in the same line, 1, 0, 0 and 2, 0, 0. I show you this. Intuitively. In 3 dimension. It's difficult for me to draw. I don't know if it's clear that these two vectors lie in the same line. I can do. Nevertheless, I try to do. Let me show. We have a vector v1, this is x, and this is y, and this is z. v1, which is 1, 0, 0. And we have v2, which is here, twice. Let me say, the length is twice, 2, 0, 0. This means if I multiply by 2 this vector here, I will get this. I will generate this. If I divide the vector by 2, I will generate the blue. Generate, the word generate. Remember at the end of this definition, the word generate appeared. Generate. But it's not the case with the vector v1 and v2, 1, 2, 3, 2, 0, 0. I do quickly this. I do quickly for you. Oh, it's clear. I do. Then we will do another exercise. Look. I copy and then I come to you. Okay. Why I can directly say that these two vectors are independent? Because, look, it's easy. With me, equals. Oh, I copy the same. I'm so stupid. let me see. I copy the same. 1, 1, 2, 3, 2, 0, 0. This is correct. It's 1, 2, 3. Excuse me. Again, they must be independent. 1, 2, 3. Excuse me for the error. This is the same. 2, 0, 0. This means 0 equals alpha 1 plus 2 alpha 2. I don't have place. I'm so stupid. Let me write horizontal. No? So in any case, it's not so. Let me write in horizontal form. This means alpha 1 equals 0 from here. Alpha, excuse me, 2, excuse me for the error. No, it's okay. It was okay. Excuse me. We can see here. This is correct. This is and this also. But we can see here alpha 1 equals 0. Did you agree? If alpha 1 equals 0, we have also alpha 2 equals 0. Necessarily. Please pay attention. Necessary. This means independent. But the reason is that basically to annihilate this component here and this component here, we need alpha 1 equals 0. We need no chance because we don't have here components. This is a little bit intuitively the idea why we knew in advance that they were independent, even though we have two vectors in the dimension 3. This means was not clear necessarily to demonstrate we need the math. Okay. If we are tired, we can take 5 minutes, not more, a little bit to finish the coffee. I would like to take 5 minutes stop, and then we will introduce the second part of the lecture, in which I try to yeah, another topic, important topic in analytical geometry. We have just 2 slides here, and then I re-upload another presentation. So I try to do today this chapter of the analytical geometry, including some exercises. I will upload also some exam exercise on this topic here, but I have here later, I think, also. I mean, we do together exam exercise. Also today we have seen this typically with 3 components, but it could be that I put just 2 components because I will come back to next week on exam exercise. But also today I would like to conclude to conclude the geometry. And then here we have just 2 slides to introduce, and then some exam exercise on the analytical geometry. 5 minutes? Okay, we will come back in 5 minutes. Let me stop recording.